Okay, so welcome to my talk in this online version of LICS, where I'll present my paper on the computational content of Zornslemma. And my slides are available on my webpage if anyone wants to download them or look at them afterwards. So before I begin, I want to briefly outline the purpose of this talk in relation to the paper, because it's very hard to squeeze an entire LICS paper into a 25-minute talk, and I'm certainly not going to attempt that today. Rather, I want to focus on just outlining the mathematical and historical context to the paper, and then presenting the main problem I was trying to solve. So I'm going to give a very brief sketch of the central ideas and the main technical problems, but nothing more than that. So any technical content I give is presented in a very informal manner. I hope it's not misleading the way I presented it, but it's designed so that it can be reasonably easily understood on a slide. And then if anyone's interested in looking up the messy details, these are of course there in the paper. So I know there's a Q&A session, but if anyone has any questions, then you can also just send me an email and I'm more than happy to talk about all this. Okay. So in one slide, this is what the paper is trying to do. So this is a work on the computational content of Zornslemma. So more generally, it's on the extraction of programs from proofs. And here I've got the two sides. So I've got, this is my proof side and this is my program side here on the right. So on the logical side, the aim is to take Zornslemma and then adapt it, reformulate it into a syntactic axiom which can then extend theories of Peano arithmetic in finite types. And this adaptation of Zornslemma is designed so that it is amenable to program extraction using the functional interpretation. And in order to do this, on the computational side, one needs to come up with a new form of recursion. So a form of recursion that is designed specifically to give a computational interpretation to Zornslemma. And as I said, these two sides, the logic and computation, are connected via Gödel's functional interpretation, one of the most important techniques for extracting programs from proofs. There are of course other ways of doing this, notably variants of realizability. And in fact, realizability has been used in the past by other authors to give a computational interpretation to reformulations of Zornslemma. So in particular, there's a paper by Berger in 2004 which looks at something called open induction over the lexicographic ordering. I'll mention this paper later in the talk, but my work here really builds on the ideas in this paper and tries to bring them to the world of the functional interpretation and generalize them slightly. And this was a nice project because there was really something non-trivial to do both on the logical side and on the computational side. So on the logical side, there was a design problem, namely taking Zornslemma in its full strength and simplifying it to a nice, clean syntactic axiom that is nevertheless strong enough and useful enough to prove a lot of the things that we are interested in proving using Zornslemma. And on the computational side, the main challenge was to develop this new form of recursion for interpreting Zornslemma, and in particular to show that this form of recursion actually makes sense, so it has a reasonable model. And in this case, a reasonable model will be the total continuous functionals of Kleene and Kreisel. Alright. So I have one slide on Zornslemma, and this is followed by one slide on the functional interpretation, just to recall these ideas. You don't have to understand the functional interpretation in any detail, and I'm also going to very quickly go through what Zornslemma is. So the way I've chosen to present Zornslemma is by focusing on strict partial orders. This was slightly nicer for the purposes of the paper. So there are two main assumptions in Zornslemma. The first is that we take a strict partial order and we assume that it is non-empty. Right? So we have a non-empty set equipped with a strict partial order. Often Zornslemma is formulated in terms of normal partial orders, but I'm using strict partial orders. And the second assumption is to suppose that every non-empty chain, so that's a totally ordered subset, has an upper bound in S. Right? If these two assumptions hold, then we can conclude using Zornslemma that S contains a maximal element. So in other words, there's some element m in my set such that it is not the case that x is greater than m for any other x in S. Alright? So this is Zorn's lemma, and in ordinary generic mathematics, it's typically used for building objects in stages. So classic applications which use Zorn's lemma is the statement that every set has a well-ordering, every vector space has a basis, every non-trivial ring has a maximal ideal, and so on. So typically we're working in some kind of world, and we want to construct something in stages in an infinitary way, sort of using infinite stages, and this is where Zorn's lemma comes in. And it's well known that over ZF, Zorn's lemma is equivalent to the axiom of choice. So it's a very strong principle, and this is one of the challenges in the paper, is the interpreting strong principles using equally strong forms of recursion. Alright, so now my slide on the functional interpretation, also called the dialectical interpretation. It's not important to understand this to understand the rest of the talk, to follow the rest of the talk, but I want to just give a brief overview just so that for those of you who are familiar with it. So the functional interpretation, it translates some formula, each formula in some given target language, and typically these are extensions of arithmetic in all finite types. So it takes a formula in the language of, let's say, Heiting arithmetic in all finite types to one of the form exists for all. Alright, so here these variables, these are possibly empty tuples of variables, and there are two key properties here. The first is that this inner formula here is quantifier free, so the translation acts as a kind of skolomization. It draws all the quantifiers out, so we have a stack of exists and a stack of for alls, and then something quantifier free in the inside. But the idea is that this preserves validity, so A is equivalent to its translation over some suitable base theory. So the functional interpretation is essentially a fancy form of skolomization, and the way that the functional interpretation brings out these quantifiers usually means that they end up being higher type, but I don't want to go into the details of this. And so Godel's classic result on his dialectical interpretation, published in 1958, and I've said essentially Godel here because strictly speaking he worked with ordinary theories of Heiting arithmetic and piano arithmetic, but extending them to theories of arithmetic in all finite types is not difficult at all. So suppose that Heiting arithmetic in all finite types proves A, then from the proof of A we can extract a term of system T, these are the primitive recursive functionals in all finite type, such that T proves that little t witnesses the dialectical interpretation of A. So that's the classic soundness proof. One has to be careful with issues of extensionality in this theory, but that's not relevant for this talk. And we can extend this to classical theories by first precomposing with the negative translation. So if piano arithmetic in all finite types proves A, we can extract a term of system T which witnesses the functional interpretation of the negative translation of A. Okay. And so applications of the functional interpretation, I mean, this was originally used to establish relative consistency, so we reduce piano arithmetic to system T, and then from the consistency of system T, we can then infer the consistency of piano arithmetic over a very weak base theory. But mainly today, the functional interpretation and other related proof interpretations are used for program extraction. So if we have a proof of some existential formula, we want to extract some term which witnesses that. And this forms the basis of, for example, the proof mining program. So proof interpretations, they come from Hilbert's program, but they're extremely important today, and they have a kind of a practical use to extract computational information from proofs. And this is why I'm focusing on, this is sort of the basis of this article, is to try to extend these ideas of program extraction to strong axioms. Alright, so just to give you a rough map of the various soundness proofs for the functional interpretation. So the original result of Godel is that piano arithmetic gets mapped to system T, but there are extensions of this in both directions. So there are refinements of the functional interpretation which take, for example, fragments of arithmetic and map these to fragments of system T, and similarly for theories of feasible arithmetic. And in the other direction there is strengthening, so that there are extensions of the functional interpretation to stronger theories. So a famous one is that of Spector in 1962, who showed that the axiom of countable choice could be interpreted by the bar recursive functionals in all finite types. And a special case of this is that arithmetical comprehension can be interpreted by bar recursion of lowest type. And so this is where the results of my paper fit in. We're looking at a strong extension of piano arithmetic using something that's kind of equivalent to the choice in some suitable way. And the question is, what form of recursion is well suited to witnessing the functional interpretation of this axiom? So that's the purpose of the paper, is to explore extensions of the functional interpretation to strong theories. Okay. So here's again the paper in one slide. So far I've briefly gone over Zornslemma and introduced the functional interpretation, and in the remainder of the talk I want to go over kind of stuff that was in the paper itself, so things that are new in this contribution to LICS. Okay. So I want to mention some related work before I go on. So firstly, the mathematical inspiration behind my syntactic version of Zornslemma comes from a 1988 paper by Raoult, and this paper looks at Zornslemma as an inductive principle, so turning it round on its head and looking at Zornslemma as a kind of induction with some additional assumptions. So induction over non-well-founded relations, which is nevertheless a valid principle because we make additional assumptions, which doesn't lead to a contradiction. Another source of inspiration is an article from 1998, which is very well known now, and this gives a realizability interpretation to both countable and countable dependent choice. And one of the really nice things in this paper is the introduction of a new functional. So this is, one could say it's a form of bar recursion, but it's quite different from bar recursion as considered by Spector. So what this is it's a form of recursion that takes as input essentially kind of subsets of the natural numbers, let's say, or partial functions. And it makes recursive calls by considering extensions of partial functions. So extensions of these partial functions with more information. So it's a kind of backward recursion that takes something that's partially defined and adds stuff to it to make recursive calls. And then in 2002, Berger came up with a nice domain theoretic proof that the BBC functional is total. In other words, it forms a total object when considered as a fixed point in the partial continuous functionals. And he uses Zornslemma to prove this. So this establishes a connection between this form of recursion by extending partial functions and Zornslemma. And then I mentioned this paper before. In 2004, he then extends this idea and presents a realizability interpretation of something called open induction. So open induction is an induction principle on the lexicographic ordering on infinite sequences. So this is a non-well-founded relation, but the induction principle works because there are additional assumptions. And he solves this using a form of recursion called open recursion. So it's a form of recursion that's very naturally connected to the induction principle. And in a sense, in a concrete sense, it generalizes the BBC functional. So these are the papers that inspired this work. And what I'm trying to do here is firstly extend this to the dialectical interpretation. Most of these papers here focus on realizability, and I want to look at the subtleties that arise when one considers the dialectical interpretation instead. And also give a slightly more abstract presentation of Zornslemma, which comes with a parameter, which when instantiated gives open induction as a special case. Alright, so this syntactic formulation of Zornslemma I've talked about, I just want to explain in a very informal way what I mean by this. So Zornslemma can be considered as something which assumes non-emptiness plus chain-boundedness and concludes that we have a maximal element. So written in one line, this is essentially what Zornslemma is. And for me, I take a syntactic principle which goes from non-emptiness to the existence of a maximal element, and then this chain-boundedness, this assumption, is somehow dealt with implicitly. So let me explain what I mean by this. So this is roughly what my syntactic variant of Zornslemma looks like, and this is directly inspired by things like open induction. So this idea of looking at Zornslemma as an inductive principle, or rather a maximum principle, so this is just an inductive principle turned on its head. This is not new, but trying to give a dialectical interpretation to principles of this kind for non-well-founded orders is something that I do for the first time. So this is the syntactic Zornslemma. Non-emptiness here is my main premise, and my conclusion is that there exists a maximal element which satisfies P. Okay? So like I said, this is just an induction principle on its head, so a minimal/maximum principle, whichever way you want to look at this. But the ordering doesn't need to be well-founded. So instead, this ordering has a specific logical structure, which I won't go into, and there's an additional syntactic assumption, so a syntactic condition that the formula p of x, this is not arbitrary, but it's piecewise. And again, I'm not going to go into details of what piecewise means, but roughly what this means is that it only looks at finite parts of its input, or it only quantifies over finite parts of its input. So these syntactic conditions are chosen so that the syntactic form of Zornslemma is valid in reasonable models. And I'm going to give an example of, a very concrete example of my syntactic Zornslemma, where chain boundedness is something that is true when we look at an interpretation of the principle. And so what I've done here is I've taken one assumption and formulated this in a syntactic way, and the other one is dealt with semantically in the background. So this is very much a special instance of Zornslemma. Its validity very much depends on the choice of parameters, so I can choose stupid parameters for which this has no reasonable model. But just to give you an idea of its strength and its usefulness, there's a simple instantiation of my parameters for which the syntactic Zornslemma on this parameter is equivalent to full dependent choice. So as a special case of this axiom, I get full classical analysis in the sense of specters. So it's a very strong and it's a very useful principle. Alright, so let's give an example of this, so a concrete example of this strange and abstract axiom. So suppose we're working with our main objects here are characteristic functions of subsets. So these are things that can be typed nat to bool, and my relation is just the strict subset relation, coded up in a suitable way. So then my syntactic Zornslemma becomes something of the following form. So it's a maximum principle, or in other words, an induction principle over extensions of, over the proper subset relation. And in this context, I take P to be piecewise if it can be written as a universal quantification over finite initial segments of my sets. So this specific instance of my syntactic Zornslemma is very closely related to Berger's update induction. And this is very useful because it can be used to give direct proofs to a number of important results. So there's a very clean and simple proof in piano arithmetic extended with this syntactic Zornslemma over the subset relation that all non-trivial countable commutative rings have a maximal ideal. And I've explored this in another paper. So these things are very nice, even very weak forms, very specific forms of this syntactic Zornslemma can be used to prove in a very concise and elegant way important mathematical facts that traditionally use Zornslemma. And in addition, one can show that both the set theoretic type structure and the continuous type structure are models of piano arithmetic extended with this thing. And this is where the chain completeness comes in. It's in the background, and we verify that yes, this subset relation is chain complete. It forms chain complete partial order in these models. Good. So what is a natural computational counterpart to this special instance of my syntactic Zornslemma? So in other words, what form of recursion can we associate with this maximum principle? Well, the most obvious is just a simple recursor over this relation. So in other words, I take as input some x, some subset x, and then I make recursive calls over proper extensions of this subset. So one issue here is that this condition here, that y is a strict subset of x, is not decidable, and I want this to be decidable if I'm doing a case distinction. But I can reformulate this in a decidable way. So I just need to find a point such that this point is in y but not in x, and then this is a completely equivalent induction principle over extensions of sets, proper extensions of sets, where the check case is a decidable property. Good. So this looks like a perfectly reasonable induction principle, but of course this is, recursion principle, but of course this is recursion over a non-well-founded relation. So the question is, why and how and when is this thing well-defined? And so here's a sketch of a result that is made precise in the paper. Suppose that the output type here of this form of recursion is a natural number. Then one can show that this recursor is a total object in the model of partial continuous functionals. And the idea is that when this output row is a natural number, by continuity, my recursor only ever looks at a finite initial segment of its input, and therefore totality can be viewed as a kind of a piecewise predicate. And so we can use Zornslemma again to prove that my form of recursion is total. Alright? So the idea is I can do recursion over non-well-founded relations if my totality predicate can be viewed as a piecewise predicate, and then I can apply Zornslemma again to establish totality. But what happens when we relax this assumption that the output type is a base type? So I don't want to go through this example in detail, but let's suppose that the output type is, say, nat to nat, so it's not a base type. Then it's very easy to come up with an example, and this is just put on the slide to show you how short and simple the example is. It's very easy to come up with a primitive recursive parameter such that this recursor is no longer even consistent with piano arithmetic, so there's no hope of finding a reasonable model. In particular, the continuous functionals, this is not a total continuous functional, when we no longer have the restriction that this row is a base type. And the problem, which is very specific to the functional interpretation, is that I need this output type to be arbitrary in order to give a computational interpretation to Zornslemma via the functional interpretation. Somehow one needs to overcome this problem. So that's a problem. We need a form of recursion which is valid for all output types and not just that of base types. And so the solution, and really I'm just going to sketch this in one line, the solution in the paper was to define an alternative form of recursion based on the idea of a truncation. So roughly what this is, so this is just my ordinary form of recursion that was on the previous slide, so it's recursion over the proper subset relation, but here I build into the recursion scheme an additional operation which truncates the input explicitly. So this can't be done implicitly using continuity, so I force the input to be truncated explicitly using an additional argument, an additional parameter. And this takes care of piecewiseness of the totality predicate. So the idea is that piecewiseness of the totality predicate is now controlled syntactically, and with this more complicated form of recursion, I can now prove that we have totality for all output types, not just discrete output types. So under certain reasonable assumptions, this altered form of recursion with a truncation operation defines a total continuous functional for any output type. And with this in place, the main contributions to the paper are as follows. So first of all, there's a generalization of this, so rather than just working over the proper subset relation, it works over a very general relation. And then I give precise conditions on this relation so that this form of recursion defines a total continuous functional. And the second main result of the paper is a program extraction result. So we take this extension of piano arithmetic, this syntactic Zornslemma, and show that given some conditions on my parameters, there is a term definable in this new form of recursion which realizes the functional interpretation of the negative translation of the syntactic Zornslemma. So it's a very general result on program extraction. It's parametrized, and I give reasonable conditions on the parameter which ensure that not only does this program extraction, not only is this extraction via the dialectical interpretation correct, but also the realizer has a model, so it's a total continuous functional. So there's the summary of the paper again. In the second part of this talk, I've briefly talked about the syntactic Zornslemma, so my adaptation of the general Zornslemma so that it becomes amenable to program extraction. I also sketched very briefly the problem that you face with the functional interpretation and why you need to come up with some form of recursion that is closely related to this inductive principle, this maximum principle, but you need some additional thing to ensure that this new recursor is total for all output types, and that turns out to be a very subtle argument. So this is one of the main contributions to the paper was dealing with totality and dealing with outputs types that may be higher types. I haven't gone into details here on precisely how this is used to construct the realizing terms or anything like that. But again, this is all in the paper, and I hope that in this talk I've just given a nice sketch of the different components of the paper and how they relate to one another. And that's everything. Thank you.